about MERLOT Reserve, which is a machine learning model that learns neural script knowledge through vision, language, and sound. It is published on CVPR on 2012 and have 117 citations. We are group 6. My name is Tony, and I will do the introduction and related work. My team member will do model architecture, experiment and application study, quantitative analysis, and the limitation and potential ideas. Before we talk about the paper, we first introduce a term called script knowledge. It is proposed by Strong and Epson in 1977. It is a body of knowledge that describes a typical sequence of action people do in a particular situations. We introduce an example of cooking popcorn. The V1 is the video frame, and the W1 is the subtitles, and the A1 is the audio. The process begins with the raw kernel scattered into an empty metallic pot, and later we turn the heat on high, and later we add a lid. The process ended with a dynamic sound of the popcorn popping. Here, this sequence of actions can be said to be the script knowledge in the particular situations of cooking popcorn. So we introduce the script knowledge. Next, we will introduce a term called learning from reentry. As a human, even we didn't see the subtitles here, and we didn't hear the sound here. We can imagine that the subtitles might be juggled while it pops, and the sound is popcorn popping. Predicting these subtitles and the audio is an instance of learning from reentry, which is time-locked correlation enable one modality to educate others. Here, the image modality educates that the subtitles and audios. It's crucial for how we as humans learn vision and word knowledge. So can we build a machine that learns the script knowledge through vision, language, and sound together? Yes, it's a MERLOT Reserve, the paper we're talking about today. And it's a multi-model event representation learning over time with retrained supervision of event. Here, the multi-model event representation learning over time is learning the script knowledge, and the reentry supervision of event is learning from reentry that we introduced earlier. Our model learn from these three modalities. When given a video, we first replace subtitles and audio with mask token. The model can predict by choosing correct mask out snippet. The important thing to note here is that the model cannot generate subtitles or generate videos, generate audios. They can only choose one in a few options. Next, we introduced related work. There are two active lines of research. The first one is joint representation of multiple modalities. The second one is co-supervision between modalities. The joint representation of multiple modalities stands for learning from image text pair or image audio pair. For example, the visual board models learn image text pair, and the predecessor MERLOT, which is not MERLOT Reserve we talked today, also learn visual text model, but again lacks audio. When we do the co-supervision between modalities, there is a pitfall. That is, complex image-text interactions are ignored. Instead, the model learns simpler text-text interactions, which is bad. And a clip come to counter-react this with objectives that cannot be shortcutted. That is, clip learn the complex image-text interactions. MERLOT Reserve, we talked today, combine these two active line research and learn three modalities together. Next, our team members will introduce the model architecture.
Hello, I'm Shomik, and I'll be giving you the details of MERLOT reserve. So we want to jointly reason over everything, including audio. Now, learning this trimodal fusion is very challenging. We need to learn fused representation of between the modalities, and now the supervision required during for pre-training is harder. So MERLOT, so what we can do is that we can predict out mask text, but how do we mask out audio? Because audio is a long range perceptual signal. We as humans abstract away from atomic level sounds, right? So we make a more semantic and higher level understanding of and prediction to supervise our learning. So MERLOT reserve, this model, what it does, it takes it gives us a solution of how to take into multiple modalities into the audio encode, the vision language audio temporal encoder. So what we do is we take in the whole video as an input across all the modalities and into the vision language audio temporal encoder, but we replace a sequence of both text and audio with a special mask so that the network at this position can anticipate not just the text that was said during the section, also the audio. Now, let us talk about the inputs into the model. So we take videos of at most 40 seconds from the YouTube temporal 1 billion dataset that we are going to talk about later. So we divide the videos into segments of 5 seconds each. So we have 8 segments per video. From each segment ST, we acquire the middle frame VT. So just this one image from a video of 5 seconds. We take WT, which is the ASR tokens from YouTube's transcribing services. So it is basically the automatically generated subtitles from YouTube. And we take the audio spectrogram AT as an input of the audio segment. So it is very important to note that WT is automatically generated from a model given AT. So WT will have strictly less information than AT. So what we do is that we provide the model with either one text or one audio for each segment, and then we mask out sections of both the audio and the segment for the model to predict during pre-training. Going into the model architecture, we use a vision transformer to independently encode each frame. We use a patch size of 16 and a 2x2 key query value attention pool after the transformer to convert an image of H cross W to a feature map of H by 32 cross H by 32. And we also add a CLS token to the input so that we can retrieve the hidden state VT at that position. We use what BP table byte pair encoding embedding table for the masked out sections of the text. We also use for the inputs of the audio segment, we divide it into 3 equal parts, and each of the equal parts are fed independently into the audio encoder. The feature maps are then concatenated together. Now, we provide the sequence level representation of the image and the text or the audio into the joint encoder. I will come into the odd section in the next slide, but we put in the sequence level representation of the image and the text or the audio into the joint encoder. Now the joint encoder contextualizes over all the modalities and the segments, and it gives us a prediction of the masks, audio mask as well as a text mask. Now, so WT here is the text mask, the AT here is the predicted audio mask. And then we supervise this learning with independently encoded segments of the audio AT as well as WT, which we get from a separate audio text encoder that they do not mention here. Now, so when we train a model to predict any perceptual modality like audio or vision, so and the input is also of the same modality, what happens is it leads to shortcut learning, which has low training loss but very poor representations. Now, we hypothesize that this might be because the model is learning a lot of imperceptible features like the model of a microphone or the chromatic aberration of a camera lens. So how do we avoid this shortcut learning? So they propose two ways to avoid shortcut learning. They train the model on two types of mask videos. One where they use audio only as the target. So they provide video frames as the text into the model, and the model infers text and audio representation in the mask tokens. Or they provide audio as the input, but in this case they provide video frames and text or audio. So they use text for 80% of the time and audio for 20% of the time, and they infer only text representations in the mask tokens. Now, since this is the first paper in the course that takes in audio as an input, so let me talk briefly about the audio spectrogram transformer that they use here. It takes in as an input a 2D audio spectrogram, and it divides it into splits into patches of 16 cross 16, and then with overlap, and then it is projected to a linear 1D patch embedding, a sequence of linear 1D patch embeddings, and we add learnable position embedding to each of the patch embeddings, and we prepend the whole sequence with a classification token, and the output of this the output patch is then input into the transformer encoder, where the output of the classification token is used to classify with the linear layer. Now let's just talk about contrastive mask span, which enables learning between the two modalities, text and audio. So we are provided with a sequence of video frames, right? So each segment has one video frame to it, and then three subsegments of text or audio. Now the subsegments of the audio are independently encoded by the audio encoder before it's fused by the joint encoder. We train the model by replacing 25% of these subsegments of both text and audio with a special mask. And the objective is to predict each of the output vectors for the mask, and then we compare it with, and we maximize the similarity with the input audio or the text. In this case, this is the text that came in for each of the subsegments. So we compare it with each of the subsegments there are, and then we maximize the similarity between them, and we get the contrastive mask span as the sum of the L text and the L audio. I'll get into the maths later in the next slide. So Zitom previously talked about re-entry in a previous slide. So let us talk. So this brings us back to the concept of re-entry. So our model, the MERLOT reserve, gives us an output, a prediction of the audio vector that it thinks was in place of the mask token. Now what we do is we encode separately in isolation the input vector for this span as well, and we get this target vector, and we get the other vectors for all the other spans for the audio that we have used as an input. Now the objective is to maximize the similarity of A1 with this A1 cap and versus all the other targets, so that the model tries to maximize the similarity between the input as well as and the output, predicted output. We do the same for the text encoder as well. It is important to note that the text encoder used here is not the same in the architecture, but they don't mention what text encoder they use. Also, the text representation go beyond just single words. So similarly, we maximize the similarity W1 to W1 cap versus all the other targets, and then we get this L mask to text where it is where we minimize the cross entropy between W cap and W cap T and WT. So this is basically so we L2 normalize W cap and WT, and then we scale the dot product with a factor of sigma, where sigma is from previous work they have clipped it at 100. What sigma does, it helps initialize warm up the models to emphasize on the hard negatives. So now L mask to text, if you get the transpose of it, we get the L text to mask, and you add them together to get the total text loss. You do the same for the audio as well, and you get the total audio loss. So the contrastive span training, that is that spans the span training for all the three modalities, which enables learning between and across all the three modalities, consists of two parts. One is the concentric mass span between the text and the audio that I talked about. And then another is they've used the result from a previous paper, contrastive frame transcript matching from MERLOT, and they name it L frame. And the total loss defined in this paper is the contrastive span, mass span, as well as the frame transcript matching. Now, we just saw how we get the L text and the L audio, but how do we get the L frame? So what we do is we match we match a frame with the all the encoded transcript of that is provided to us, and that in turn supervises the frame encoder, so that we can learn without using any human level data. So the total loss here is the symmetric total frame loss between the transcript and the frame, and the frame and the transcript. And this is how we get the total contrastive spanning loss for the paper. And the pre-training and evaluation study and experiments will be taken over by the
Hello everyone, I'm FT. I'll be taking over the pre-training ablution studies and limitation and potential ideas of the paper. So the authors propose two variants of their model. One they call the reserve base and the other the reserve large. So reserve base has a hidden layer of 768 dimensions. It has a 12-layer vision encoder, image encoder for image encoding, 12-layer joint encoder, and reserve large is basically double the size of reserve base that they propose. So in the training setup, you can see that they use 512 like TPU cores, and like they train reserve base for 5 days, reserve large for around 16 days. So then they also propose a data set of their own, which they call the YouTube temporal 1 billion. And in this, like they have 20 million English subtitle YouTube videos. The English subtitles come from YouTube's own ASR. They have 1 billion frames. And like they use this to pre-train the model actually. And one of the things is the reason they propose this data set is basically they want a large data set in the scale of like JFT for still images. So among the ablation studies, one of the things that is required is if we want to like understand how well a model does, we need to train it for pre-trained tests, a downstream test. So in this case, the authors they propose a downstream task which through a dataset called VCR or Visual Common Sense Reasoning. In this case, the model is provided with an image and an answer with 4 choices and a rationale, which is basically the reason why the model is choosing a specific answer. And in this case, they also have 4 answers. So based on their like choice of answer and rationale, the model is evaluated. So basically, after one epoch of pre-training, the authors actually like compare every single modules. They introduce every single modules of their model one by one, and then compare it with popular masked language modeling approaches. At first, they only introduce text contrastive span, and they see a 2% around 2% improvement. Then they, based on what Shumik said, the shortcut learning, they introduce every single segment of the shortcut learning one by one. As you can see, audio as target, they get a certain amount of improvement. Then they add audio as input and target. Then they get a certain amount of improvement. And in case of their data set, one of the things that they found out was like if they remove strict localization, which like is when like the alignment of the audio and the text, they would actually get a loss in accuracy. And at the end they have a 1% improvement. This is from training the joint encoder of their joint encoder with extra web scale data. And then like one of the things that the authors mentioned is like they would have gotten an improvement in their training, but they had limited computation, so they only trained the model for 10 epochs. So as you can see from here, like reserve base and reserve large actually does well. Like when they add video based data, including audio, they see that they perform better than like popular models that are industry grade, like Unitar, Arni, which are around 10 times their size. And so from this, what we can derive is like the authors derived was that like even though this is an vision and
text-based task, audio actually helps it achieve better accuracy overall. So after this, we have TVQA. And so in case of TVQA, it's very similar to the VCR task, but in this case, the authors, the model is provided with a video, a question, and an answer. And this video is these videos are of popular American shows. So in this case, the dataset also has audios. So one of the things is existing works, they only use the video frames and the text for training. But in case of Merlot, they also use the audio. And as you can see, like at the start, like if they they only train it with subtitles, but then they add audio, and like as you can see, there's a clear improvement. And then when they add both, there's an overall around 1% improvement. So audio actually helps here, as they find out. Now, one of the questions that comes in is, this is good and overall, but how does it actually compare, and how does Merlot Reserve perform in only vision-based tasks? So in this case, like the authors took activity recognition as a representative for computer vision task, and in this case, they took the dataset Kinetics 600. Now, Kinetics 600 is a dataset that contains 10-second videos of action-based tasks over 600 classes. So they train this model with only only vision, and then they also train this model with vision and audio. And in case of this, they use no transcripts at all. And when they compare it with previous models, you can see that adding audio actually helps around 1.7%. And then like another thing that the authors did was like they performed a zero-shot experiment on this to actually understand the zero-shot capabilities of this model. They proposed like 4 data sets for this. One is the situated reasoning data set. This is short situations of videos. The model is provided with a question and 4 choices. But one of the things is they're not provided with an answer. So the authors actually use a template-based method to generate answers and then like evaluate the model. So as you can see, like in all these cases, we can see that like if they train it with audio, they do better in case of Star. Then there's Epic Kitchens. In case of Epic Kitchens, there's like the model is provided with a video, and like they have to predict class, and the videos are like of long tail distribution, rare classes are more. So this is also very challenging. In this case, we can see that audio helps. There's LSMDC, which is where the model is provided with a video and a description, and the model has to predict fill in the blanks. So in this case also they are doing well. And in the last case, there's open-ended video question answer. So this is basically, in this case, the model is it's basically video-based open-ended question answering. So in this case, also the model does better with audio. Then one thing that the question comes up is qualitative analysis. So why does audio help? Like the model is provided like in this case, what the authors did is they test the model with an input, which is basically like they cherry picked 3 cases from their validation set, where the model is provided with a frame and a corresponding text, and like it has to predict audio and text. So basically, like based on the mass token. So this is actually like they cherry picked 3 specific cases which might occur. So in this case, you can see that like the amount of audio and the amount of text is the same, right? But as training progresses, you'll see that the text part is being predicted as well. But in case of what the model chooses to do is like it actually tries to associate the masking part with basically like all like uh, uh, basically predict it totally accurately, because one of the things is like although there are popcorn poppings surrounding it, in this case, in this span, it will learn popcorn popping more. So another case that happens is like that might happen is like we will see that audio might be there might be a lot of audio and the text might be very less. So in this case, what is happening is like this girl is like talking about her parents, and like the presenter, and she wants their respect, but the presenters think that she's rude, so she's rude, so she will the presenter actually laughs and asks why would they respect you. So basically in this case what happens is like it learns to associate the audio part and also another thing is like I'd like to mention is in case of the text part. So basically, like as it progresses, the model also learns to associate audio with text too. And in the last case, what happens is like there might be a case where the audio isn't present. Like in this case, the yogi is given instructions, there's subtitles, but the video is muted, right? So in this case, like we wouldn't want the model to hallucinate. So like as we can see, like as the training progresses, the audio tokens are predicted, like there are no audio tokens predicted, the span is matching. So in this case, the model has hallucinates less as it progresses. So like we can see that there's a lot of metrics and the model is doing well and all, but there are some limitations and like some potential ideas that we thought of like when we read the paper. So one of the things that came up was like the authors, in case of YouTube Temporal, what they did was they provided a lot of links, but they didn't provide the videos. And one of the things that came up was like, so reproducing the dataset itself is very hard because like some of the videos might not be there, some of the videos might be hidden, and there's also a bit of privacy concerns, like how much privacy, like how many steps were taken to actually like understand the privacy of the users videos that were used. Another thing that was like the noisy text was used in YouTube's automatic speech recognition. So as we can see that noisy text being used in it can actually affect the model and capability to for downstream tasks. So another thing that we saw was they were using, for every 5 seconds they were using a single frame per segment. Now this is very bad because a single frame is not representative, might not be representative of the 5 seconds. It might be better to like somehow do a cheap learn poly mechanism or like a learned representation of all the frames in the segment. Another thing that we can see, like if we have seen the last classes, like many of the models like Mammoth, then Coca, all models normally they have a generative component to it. So basically, like if we add a generative component here, that might actually help the model like understand, because like as you might have seen, the loss that's here used here, contrastive span training, it's only a contrastive loss. The generative component might help it do better. And another thing that we'd like to mention is the model can only access 40 seconds of video. So basically the thing is the input is actually 8 segments and like each 5 segments. So 8 5 are 40. So one of the problems that this might be is that like if it was used in a long video understanding component, the model might perform very bad actually. So that's all from us, I guess. Thank you very much.